Today, I'm going to talk about 5G technology. I will cover the engineering requirements for 5G, the comparison with 5G and 4G, and the 5G key technologies. The 5G engineering requirements can be set with these objectives. A data rate where 10 gigabits per second or more is supported in the cellular area. In addition, 1 gigabit per second, even at the cell edge, which is the location where the performance is worst. The spectral efficiency we want to boost up to 10 bits per second per hertz. So in other words, if you are given like a certain amount of bandwidth, then you can see the data rate of how much you should get using the new high spectral efficiency modulation techniques. In addition, considering vehicles, Internet of Things, smart devices, wearable devices, smartphones, and so much more within a square 1 kilometer area, we want to be able to support 1 million devices. A tremendous amount of connectivity that's being supported is one of the objectives. In addition, we want very small latency for end-to-end service. From the moment you hit your request data button, the data is delivered to you within 5 milliseconds. We want 5 milliseconds technology, and when you just look at how long it took to get over the access point to the device or the base station to the device, we want that to be less than 1 millisecond. Let's take a look at 5G key technologies. First, advanced networking technology. We want flat and distributed network architecture. We want an integrated and distributed network function. We want it to be a programmable network architecture that uses SDN, software-defined network, and NFV, network functions visualization. Let's take a look at software-defined network, SDN. SDN decouples the network control and data forwarding paths and functions. Distributed management by using the shortest data path without traversing the core network is what we would like to accomplish. Now, network control can be directly programmable, and this flexibility provides us with so many enhanced features. The underlying infrastructure is abstracted for applications and network services. NFV, Network Functions Virtualization. NFV is a technology used to virtualize complex hardware-based network node functions into software building blocks that can be combined and trained to create advanced communication services. So in other words, what used to be in one system block, we look at those functions, we take them in to design this into building blocks in software, just like Lego pieces. And we combine them based upon how we want to use them. Now these components are what we are looking at in NFV. NFV eliminates dependency on complex hardware-based nodes by using flexible software blocks that are called VNFs, virtualized network functions. It provides improved flexibility and improved functionality and improved efficiency. Now I'm going to compare 4G, the LTE network, to 5G. And I'm going to briefly talk about 4G LTE architecture, so I can make the comparison of how 5G is making progress over existing 4G technologies. The LTE network has a hierarchical core network architecture, as you can see. It has the overall system that's connected to the internet, is what we call the EPS, the Evolved Packet System. And there is a U-chain, which is the Evolved Universal Terrestrial Radio Access Network. That's where the base stations are connected through, and they provide mobile wireless access to our smartphones and our other types of phones that are mobile devices. Now, in this architecture, all terminal traffic is tunneled through centralized nodes, such as the serving gateway or the PDN gateway that we have up there. And these controls are connected through the support of MMB, HSS, and PTIF modules. Now, high end-to-end latency, high backhauling load, low reliability are some of the results that could come when these networks are overloaded with too many users. Now we have the P gateway, which provides these functions. Then we have the serving gateway, which provides packet routing and forwarding, mobility anchor for inter-InnoB handover. But when you go into more advanced handover, basically the IP address allocation to the EU and also mobility anchor for non-3GPP handover combined between 3GPP and non-3GPP handover. That's what the PDN gateway supports. The other components within the LTE 4G network are the MME Mobility Management Entity, which supports mobile roaming, user authentication, and controls the process of the signaling between the UE, the user equipment, and the Evolved Packet Core. Then there is a HSS, Home Subscriber Server. It's a database containing the user subscription information, and then the PCI, policy control and charging rules function. Now in advanced network, what we want to have is a flat distributed network architecture. Distributed management providing the shortest data path without traversing the core network is what we want. So we want these features, and in addition, we want content-aware resource allocation considering real-time traffic service type and device characteristics. Popularity-based content caching using content delivery network techniques for latency and packet traffic reduction. And as you can see, Stadium technology that I mentioned before, it's going to be used over here. One of the things I said before, as a target, we want to have less than 5 milliseconds of end-to-end latency, which means that on my smartphone, when I request for contents, a certain information I want to be delivered to me within less than 5 milliseconds. In order for that to happen, the contents must be predicted and brought to somewhere close so that as soon as I ask for it, it's delivered to me. That's supported by Stadium technology. Now we have millimeter wave systems. There is huge bandwidth available at these high millimeter wave frequencies, which are about 6 GHz, and compared to the current LTE band, we can gain so much more capacity. For example here, 2.2 gigabits per second of a data rate can be supported by the 28 GHz band using multi-cell and 500 MHz bandwidth transmission technology. In order to make this possible, we need supporting technologies such as 28 GHz polarization interleaved array techniques. In addition, we could use like 60 GHz 360-degree covering 16 chain CMOS RFIC techniques. So above the 6 GHz range, look at some of the frequency regions that are of interest, such as the 28 GHz, the 39 GHz, and over there using a combination of Wi-Fi based upon the 60 GHz range. Now these regions are going to be used by Wi-Fi, but 5G technology is focused on using both these radio access technologies to combine all forces together to achieve extremely high data rates. So the 60 GHz Wi-Fi techniques will also be poured into the range of serving 5G technology. Then comes the multi-rate internet working techniques based upon combining former technology, which was the other Wi-Fi and the former 4G and 3G technique frequency bands. The focus here is for our user equipment UE network-based multi-rate coordination technology to pour in former resources and resources that we have from other frequency and transmission techniques. We want throughput and connection reliability enhancement using unlicensed and licensed spectrum coordination. We want internet working and integrating with a 5G system and with other radio access technologies such as the 3G, 4G, Wi-Fi, Bluetooth, and the other techniques as well. Now, data rate enhancements using 4-dimensional MIMO is one focus. In addition, spectral efficiency enhancement using multi-user MIMO, energy efficiency and data rate enhancements using virtual MIMO, and COP, coordinated multi-point MIMO supported techniques. Coordinated multi-point technique. This improves the coverage of high data rate, cell edge throughput, and system throughput. COP coordinates multiple e-node bits to communicate with the user equipment. We want to increase throughput by reducing inter-cell interference, and this is accomplished by the COP techniques down here, where we have CS, CB, JT, and DPS. CS stands for coordinated scheduling, CB stands for coordinated beamforming, JT stands for joint transmission, and DPS stands for dynamic point selection. And these are the references. Thank you.